Magandang hapon, maglang people. We are going to jump right in. Salamat. All right. So I don't speak any Tagalog, but I always hear that my accent's pretty good with it. Magandang hapon, magandang gabi, kumusta, mabuti, salamat. See, like I know little bits and pieces. We're sketching this function. Cool. Anybody brave enough to share your work? I can show you the graph if it makes you any braver. Let's check. So let's see. I know the end behavior, and I know the graph. I'm going to be real chill with this. I'm going to steal a couple of them. Okay, so I'm going to have an immediate question. How many points did you guys find? You found extra points? So we'll see. I know that, okay, so here's what we had left off with. I'll tell you just at first glance, yep, looks like it's me. I'm pretty sure of it, and I can see that it's going to happen. There's no scale, so I don't know how accurate this is, and that's okay, because we're just sketching. Anybody have a graph that's wildly different? Yours is wildly different. Can I steal this for a second?
Yeah, mine goes
Okay, so let's check.
That might be wrong, though.
So, I think so, but we're going to see why. This graph also has the same sort of general shape, right? Both of these are the up and squigglies, but there's a fundamental difference. This whole idea, multiplicity, we're going to write it a little bit differently. If the multiplicity was 2, and I can tell that from this factorization, it has 2 roots right here. It means it does what? It touches and turns around. So it should look like this. The fact that you found them is awesome. The big question is, how do we fill in this middle part? And there's a way to do this. I can't tell if you got points or not. Did you get any other points, or did you just find them and you just kind of drew it because you figured it looked like that? Okay, and I'm good with that. Anybody have a graph that's wildly different? Yours looks about like 80 meters. Not 80. That was the first time it's happened, Fern. So yeah, we see these two possibilities. Now, I'm going to show you the way that I do it, and I want you to be aware that the book does not do it exactly like this. Okay. So when I'm looking at these, I know a few things. I'm going to add one more little comment, and we're just jumping straight in. Instead of just saying what the multiplicity is, which it's important that we have that word because we're going to use it again. I don't want you to forget it. I know that if it's even, it touches and turn. Touch, turn. And if it's odd, it does what? Cross. Now, here's all I really worry about with this. I know, and this is kind of sneaking ahead a little bit, but you guys have probably never heard of what is called the intermediate value theorem. Does that theorem ring a bell? IVT, intermediate value theorem. What does intermediate mean? So, between, and I love that idea. Between, so check this out. Polynomial graphs, we said 2 things about them yesterday. Can you tell me one of them? Like me in my younger days, very smooth, right? Like smooth and continuous. So check it out. You guys have never heard the intermediate value theorem, and the true value of this isn't going to be crazy important to you right now, but I promise mathematically it means a lot eventually. We have a polynomial function, hypothetically, that goes from -4 to +8. What can you guarantee I crossed over? So at least that, literally every single point in between, right? Every intermediate point or value, intermediate value theorem, was used. Every single one of them. Now, the reason that we're tying this all together is I'm going to show you the way that I graph it and the way that I think these out, because I know that eventually I'm going to use these for calculus stuff, but then we should take a look at what the book does too, because it might make more sense. Here's what I do. I know a function can only go from positive to negative at its x-intercepts. Do you guys agree with that? If it's a polynomial, the only way it would change from positive to negative is if it has a root, a 0 solution, and x-intercept. So when I'm thinking about these, here's what I'm going to do. I'm going to make a little number line. And I know it feels so bizarre compared to other stuff that you've done. Maybe you solved inequalities like this. The only place that this function is ever going to change from positive to negative or vice versa is where? What are the roots, the zeros, the solutions, or the x-intercepts on this function? 0, so I'm going to put a 0, and 2. Now check this out. If I make the claim, I've cut this number line into 3 intervals. Do you guys understand those 3 intervals, and you get what I'm saying? Okay. How many pieces, if those are the only 2 cuts that I took on an infinitely long line, How many pieces do we have? 3. Those pieces are my intervals. Negative infinity to 0, 0 to 2, and 2 to infinity. Now, here's the really cool thing. In any of these intervals, there's infinitely many numbers that you could pick. Is there an easiest number that you could plug into this function? Whether it be here, or I guess we didn't have the factored version, but what's the easiest thing you could plug in here? So 0 is really the easiest, but it's already taken. Is there a number between these, or in this interval, or in this interval that's super easy to plug in? 1 lives in which interval, left, mid, or right? So check this out. I'm going to change color very specifically because there's a few things that happen. I know that if I plug in a 1, let's just check. And I don't like that. I'm going to change color. 1. If I plug in a 1, what's 1 cubed minus 2 times 1? So it's negative 1 is what it winds up being because it's 1 minus 2. Do you guys agree it's just negative? Like, it's a negative 1 when you actually plug it in, but can we agree that it's negative? Okay, so this is the part that I'm really focused on. I'm cool with it being negative 1. The negative is the most important part. Now, if I wanted to, could I pick something in this interval as well to plug in and see? Like, pick something between 2 and infinity. 3 is a good choice. What's 3 cubed? Okay, minus, let's see, that's 2 times 9 is 18. So it winds up being a positive 9. Check it out. I didn't even have to do that, actually. I'm okay with it, but I'm going to show you something. These were both, why did I put 0 and 2 on here? They were the intercepts, right? What was the multiplicity of this root? It was a 1, right? So that's odd, which means it crosses. If it was negative here, what does it have to be here? And if it was negative here and it touched and turned because it had a multiplicity of 2, it's positive or negative over here? Negative. This is going to make crazy inequalities like a million times easier to solve as long as we don't forget this idea of multiplicity. Now, realistically, the only value that I care about was this 1 right here. 1, negative 1 is what we spit out, which means when I go to graph it, I know I need 3 points total. I'm going to add a 0, which I think is here. I'm going to say here's 1 and 2, so there's my other root. And then before we did anything, I know end behavior says down like this, down to the left, up to the right. Do you guys agree? So then all I have to figure out is what goes on in here. I know that it stays negative after 0, and then it changes to positive where? Careful. If I want to put the point 1, negative 1, I can. But check it out. I know that it's negative, so it's underneath the x-axis up to 0. Then it is negative afterward, which means it must go up and do what? It has to turn around. There's no other option because it has to stay negative. So I go up to the axis, I turn. Now, I actually got the value, so I knew it was this point. Now, it's going to stay negative until it gets to which x value? 2. Now, this does it, and now it's here. The thing you need to be aware of, because of the fact that these are sketches, based on just this information, is it possible that this graph did something like this instead? Maybe it's 1, negative 1, but if I plug in another value, it does something like this. So it actually goes way lower than this. Is that a possibility? Absolutely it is. The more points you get, the better true graph you're going to obtain. But as far as just a sketch goes, I don't even need this negative 1. The fact that I know where it's positive and negative does it all for me. Should we see how close this is to the real graph? Okay. Desmos. Somebody tell me the function x cubed minus...
2x.
Okay. X cubed minus 2x squared. Hey, look, it looks like that. And check it out. Here's that 1, negative 1 value. And this was a total guess, just so you know. Like, I didn't prep this early. It does happen to go lower. Its lowest value happens here, but I don't care if we're just sketching it. Should we sketch one more?
Yeah, how do you know about the touch and turn?
So, like, whether it does or doesn't?
Yeah.
If a root shows up 2 or 4 or 6 or 8 times, then it is going to touch and turn around. And the way that you pick that out is when you factored this yesterday. If you factored it, it factored like this.
Yeah.
This factor that has a root of 0 when we set it equal to 0 shows up how many times?
Twice.
Good. Its multiplicity is 2. I know the graph will touch and turn here. This one only showed up 1 time. If I had done this, how many times does that root show up?
What?
If I put a cube here.
3.
but it would still touch and turn.
Even if it's not even.
So if it's odd, it crosses. This would cross. I'm sorry. That was my bad. Okay, let's do one more. Let's make up a function together. Ugh. Cool. And then I'm going to need you guys' input because I think I want to do a little bit of stuff. We're going to jump forward, and it's going to make the homework practice weird, but it's for the benefit of people who are traveling. On B, let's check it out. What's your favorite polynomial function? Cool. All right, so let's do the following. I want to graph y is equal to 2x to the third plus x squared minus x minus 1, I think. Anybody know what it looks like off the top of your head? Yeah, me neither. Okay, I think we're going to be all right. Let's check it out. I think we're going to be okay. I'm pretty sure of it. Now, we're going to do end behavior and stuff, and we're going to find the zeros. I want you guys factor this for me first. Feels like you don't know how to do it? Maybe you do. I guarantee you do. Remember when we group trinomials? We're doing that so we can write something with 3 terms with how many terms? When you do the whole grouping process and you find your magic numbers, you take a 3-nomial and you write it with 4 terms instead. How many terms does this guy have? Am I losing you guys on that thought process? And don't do this one. If I had this, my magic numbers that multiply to be 4 but add up to 5 are these. So when we're grouping, you might do this. X squared plus x plus 5x plus 4. We just took a trinomial and rewrote it with how many? 4. And the reason we do that is so we can group it, right? How many terms does this one have? So what might work? Try to group it right off the bat. See if it works out. I'll give you a second. That these 4 terms exist, we can group it like this. All of a sudden, this problem that looked kind of hard before, maybe it still looks kind of hard, but I hope it's less challenging. These groups are special. I'm going to change one thing. We're going to make it a 2x here. Yep, I'm going to make that a 2x, I'm sorry. Minus 2x minus 1. So it works out nicely because I'm just making up a random one. Minus 2x minus 1. So I'm going to fix that. All right, what would you take out of this first one? X squared. What would it leave behind? Okay, now whatever I take out of the other group better leave behind 2x plus 1, right? What should I factor out then? Say it again. Negative 1? Did you say negative 2? I still can't understand you. I'm sorry. Negative 1. Okay, love it. That's what I'm going to do. Which leaves behind a what? 2x plus 1. I see 2 factors now. One of them is what? I heard x squared minus 1. And the other one? Are we done? No, enthusiastically we all say, because I'm going to look a little closer. I can't factor the second one anymore. 2x plus 1 is just going to chill. What about this one, though? There's no GCF. Is it a binomial? Is it a difference? Do you know the square root of both of them? Can we factor it? That thing is really loud today. How does this difference of squares factor? Good. X plus 1 times x minus 1. That's that difference of squares right here. And then we still get our 2x plus 1. Okay. With this in mind, I'm going to do 2 things. EB stands for what? Good. And I'm going to write root this time, even though we could write zeros. Doesn't really matter. Okay. I have what degree for my original function? It's a 3rd degree. Is that even or odd? Okay, so I'm already thinking just y equals x. That's my first thought, because that's an easy odd. It looks like this. Okay, leading coefficient, positive or negative? Positive, which means it still looks like this at the ends. I know the end behavior informally. It goes down to the left and up to the right. Now, if you'd like, and you don't have to, but we could say as x approaches negative infinity, f of x approaches negative infinity. That's what's happening. As x approaches positive infinity. F of x approaches positive infinity. I can write it in one statement. This is saying the exact same thing as these arrows. What are the roots? -1 from here, okay. +1 from there. -1/2 from the third one. Is it okay if you need to do scratch work to set each factor equal to 0 and solve it? Riley, where did I, what's up? Which, the roots? So check it out. You will, are you okay with these factors? Now, if I'm looking for the roots, I set this equal to what? So we would set each factor, x plus 1 equals 0, to get our -1. We would set x minus 1 equal to 0 to get this. And 2x plus 1, when we solve it, we get -1/2. Okay. Now, I have my roots. Cool. What's the multiplicity of this one? Let me rephrase that question. It's the exact same question, but I'm going to take out the ugly word. How many times does this root show up? Once. How many times does this one show up? And this one? So the fact that all three of those have an odd multiplicity of 1, it means the graph touches and turns or crosses? Cross. Every single time it crosses. I know it's going to happen. Now, because we're just doing a sketch, the general shape is going to suffice. I'm going to make a quick number line, and I'm going to do one thing more specific than I did before, just to develop a good habit. What's the name of our function? It's y. So I'm going to write, and I should have called it f of x. I'm going to write f of x here, because I want to look at these values of f, and eventually we'll add more to it. What are the only numbers that I care about putting on the number line? The roots, and make sure they're in order. Which of these is the furthest left? Okay, so check it out. Here's -1. The next one that we hit, -1/2, I think. And the last one is a +1. Do I pay any attention to the scale here? Not even a little bit. I didn't check at all. 1 should be here if we're paying attention, but I don't care. It doesn't matter to me. Now, the reason I put f of x here, make it a habit. Try to put the function you're talking about. How many intervals did I cut my equation into? 4. I have -infinity to -1. Something happens, and it's always the same something. Between here, something happens. 3 and 4. There's a 4 of them. Of those 4 intervals, is there an easiest one that has a number within that's easy to plug in? That was a lot of language. What's the easiest number we could possibly plug into this function that's not one of the zeros? 0 is the easiest choice. 0 lives here. So I'm going to change color. 0. Now, you could do all of them, but we don't need to. If I plug in a 0, and I want you to notice something. If I said plug in 0 and tell me what you get, do you plug into the very beginning or one of these? If I said find me y of 5, where would you plug in? The orange? Okay. This is equivalent. We could plug in here just as easily. If I were doing 5, I would rather plug in here because I don't want to do 2 times 5 cubed plus 5 squared. We could, like it's ugly, but check it out. If we plug in a 5, 5 plus 1 is 6, times 5 minus 1 is 4, so we're at 24 right now, times 11. Ooh, that worked out really nicely. 264 would be the value because of the 11 trick that we learned last week. If that's going too much, that's okay. We'll hit that again. Here's all I really care about. If you'd rather plug into the top one, that's fine. If I plug in a 0, does it give me a positive or a negative? 0 plus 0 minus 0 minus 1. Negative. It's actually -1, but I don't care. The fact that I have just this one. All these roots are odd multiplicity, right? Which means if it were negative here, what is it guaranteed to be here? And if it were negative here on this interval, and then on this interval, by only getting 1 point, we get all of this. I know that it crosses, which means it's going to change sign. Cool. Does it seem like we have enough information to graph this yet? Lots of variation, lots of blank faces. That's okay. Let's try it. I'm going to make my graph, and it's not going to be perfect to scale, but that's all right. What numbers do I need to put on here? -1. So I'm going to try to stay consistent. -1, -1/2, and positive 1. These are my 3 roots. Everybody on board with that? Now, if we only look at the end behavior, guaranteed this thing does this at the end, down to the left, and on the right side it goes up to the right. All that we have to do now is fill in the in-between. But I know what happens. I just don't know exactly how tall it gets. Here, does it cross or turn? So it crosses, and then it has to cross here as well, right? So it probably has to come back down at some point. Then this stays negative until when? Careful. So check it out. It's between negative 1/2 and 1 is where it's negative, right? So all I know is that it crosses again there, and there's our graph. It's a sketch. This thing could do some wonky stuff in between, but as far as the sketch goes, this tells me the whole story. Does this seem easier than graphing by making a table and doing all that stuff? For sure. Okay. We have one more little thing to talk about, and then we're going to get a head start on tomorrow's stuff, I think. Before we move on, lingering questions. Something that we went through that I said too fast, I said it in too fancy or not fancy enough language. Any part of this that felt like, ugh.
This is probably only a question for me, but where does the negative 1 and the x squared go? Like after that?
So right here?
Yeah.
So this is, I recognize it as a difference of squares, which is one of the binomial shortcuts, and that factors as this.
No, but right above it, like the x squared that's outside.
Oh, this one?
Yeah.
So when you're factoring, this winds up being a factor, and then as long as these inside pieces match, that's also a factor.
Right.
And I'll go into the why here in just a second with you, okay? All right, last little thing, we're going to get a theorem, which this I think is the first theorem that we've seen this year. Maybe Pythagorean. Okay, last little thing for today, and I don't even have my notes, but that's all right. We're going to look at this big important idea called the intermediate value theorem. You will never see me write this again. The intermediate value theorem. And I use THM for theorem, just so you guys are aware. Intermediate value theorem. Now, for this, it is really, really important that we have a smooth continuous function. So we're just going to assume that we're working with polynomials right now. Given a polynomial function, which I'm just going to use the word poly, and you should rather, I'll write it so I don't go faster. Given a polynomial function, p of x, and two real numbers, a and b, we have the following. Now, we're going to make sense of this with a graph here in a second, and it's going to be super obvious once we have the graph. If you give me two numbers, a and b, that are different numbers, which we'll just work with that assumption. If p of a, that was a weird way to do that. If p of a is less than 0, and p of b is greater than 0, so one of them is negative and one of them is positive. That's all we're saying. Then a root solution x-intercept, whatever you want to word it, must exist between which two values? Good. Between x equals a and x equals b. If you give me two values on a polynomial function and one of them is negative and the other one's positive, guaranteed there's a root between them. Graphically, it is immediately clear, I think. If you want the graphical version of this, here's, nope, I'm going to make it so I can see a negative as well. Intermediate value theorem, and I can show you my notes here in a second. Okay, so check it out. I don't care where it is. P of A. I said less than 0 here, but is that required? Could it be greater than 0 here and less than 0 here? Okay, so I'm just going to arbitrarily, I'll follow this. Let's say here's A, and here's P of A. And then over at B, we just require that P of B is above, so I'll put it up here. Here's my other point. Now, this is going to be a polynomial, which means I'm going to be able to draw from there to there between those points without ever picking up my pencil. That's a fancy way of saying what? Not smooth. That's not the part that we're after right there. Continuous. It is continuous. Now, as long as I'm going to draw a smooth one and continuous, it could do something like this. It could do something crazy. More naturally, though, I think it's probably easier to say something like this if we just draw it as a smooth curve. Do you guys identify that there's an x-intercept here? And it's between which x values? It's guaranteed to happen, right? Like, it's obvious as soon as you draw it. Now, the real theorem says, instead of saying there's a 0, this is just how we're using it. If I had a function, and I'm going to draw in green, don't draw this one down. If I gave you a function that's a polynomial, and I said, hey, check it out. It starts here at 1, 8, and it ends at, in our purposes, 3, 2. And I asked you, hey, somewhere in here, does there exist a value where P of that number, X, whatever it is, equals 5? Does that exist? Is there somewhere on this graph guaranteed that it has the Y value of 5? Because literally every intermediate value, every value between those two must get hit since I can't pick up my pencil. 100%. Intermediate value theorem says it does exist. Now it could be like lame and be right here. It could be anywhere on there. That doesn't tell us anything about it, but it does tell us it exists. Okay, I'm more concerned with the fact that zeros exist for this purpose. Okay. Yay, nay. We don't have the ability yet to really use this in a super meaningful way other than saying, is there a root and how do you know? If it changes signs, you know there's a root. That's it. All right. Here's my question for you guys. I'm going to give us, I think, time tomorrow. We'll just do a bunch of homework in class tomorrow. Because I want to take a little step forward into the next step so we can at least talk about it. That sound reasonable? It's going to be weird, but I want to make sure we can start talking about stuff. So I'm going to save this picture. Tomorrow will be all work. I'm not going to give you homework tonight then. All right. And I'll actually come back and do that in a minute. We'll do this first. Okay. We're going to use the scratch page. Oh, jarring. I don't know how to delete it all. All right. There's not going to be graph paper, which is going to make it weird, but that's okay. All right. We are going to really quickly, and this is going to be a strange video break, but that's all right. We're going to start the next section. So we're going to start 2.3. And then tomorrow we'll get practice with this. 2.3 deals with polynomial division. Was it this class that we used a little bit of Snoop to help us through a problem, or is that physics? Did we talk about Snoop in here? All right, I think we did. And you'll see why I think that here in a minute. Okay, before we do anything else, I want you to do the following for me. By hand. I want you to take 315 and divide it by 31. By hand. I'm going to give you a moment. What do I do? Long division. Okay. Well, what's the dividend and what's the divisor? Love it. 315 is my dividend, the thing that's being divided. 315, and then I'm going to draw this fancy division box, and then my divisor is what? 31, and I'm going to do this to get my answer to a division problem called the quotient. Now, there's a bigger connection here. Obviously, we're going to be doing long division with actual functions, but the same idea applies. And I need everybody's ears and eyes wide open as we do it. How do you start this? Okay, so I think the way that I learned it probably is similar to yours. My first question is, does 31 go into 3? Do you guys write a 0 here? You can or you cannot. I don't care. I don't normally. Okay, so the next question then, does 31 go into 31. Does it? Once. So I put a 1 here, and then what do? I'm going to do 1 times 31, right? And then I'm going to put it here, and you probably don't do this, but I want you to make it a habit. I'm going to put parentheses around it. The reason we put parentheses around it is going to be clear in about 5 minutes. But what do we do with these numbers now? Subtract. I'm going to subtract, and it's 0, right? Okay, in the words of the poet laureate Snoop Dogg, I take this 5 and I do what with it? How? Like it's hot indeed. Okay, goes down. All right, now what? So not yet, I won't. There's a question I have to ask first. Does 31 go into 5? Nar. Okay. Which means this one, do I have to write it?
Yes.
For sure. Okay, now at this point, we could go further, right? We could add a 0 if we wanted decimals. I'm not going to. I'm going to stop here. Because I want to see what happens here. If I said, hey, what's the answer? 315 divided by 31 is equal to what? What is this? How would you express this answer? Imagine you're in 4th to 6th grade again. I don't know where it happens. Yo. Oh my gosh. Did you guys ever write 10R5? Yeah. It's 10 with the remainder of 5. Okay, I don't care about the decimal part. We could keep going. There is a decimal. Some of you may remember seeing this. Some of you might not write it exactly like this. Do you agree that there is a 5 remaining after I try? Okay, this is going to be incredibly important. I have an initial follow-up question that I just want you yes or no. Just go with your gut. Is 31 a factor of 315? Why? How would I know? Ooh, louder. There's a remainder. If it were a factor, what would the remainder be? 0. I'm going to make that statement big and important. 31 is not a factor of 315. Do you guys remember the shorthand for because? That's a good one, but it's actually this. Because the remainder is not 0. Okay. All of a sudden, this idea becomes a big one. If it were a factor, there'd be a remainder of 0. I want to do one more just with numbers, and then we're going to jump into making it a little bit more complex. I'm going to switch this question. I'm going to ask the following. Let's try this goofy number. I want to know instead, is 9 a factor of 351? Now, I will tell you the approach to this that I would like you to take is written directly above it. If it's a factor, what do you know is going to happen? So, yeah, check. Do the division, see if the remainder is 0. And I would practice here, and I'm going to even go further. I want you to find me the quotient, and the remainder I think is 0. But I want you to find me the quotient. And I'm going to do the long division as well, and we'll race.
Do you mean 351 or do you mean
351. So 9 goes into 3 0 times, goes into 35, what, 3 times? 27. Did I say 315?
On the top, it's 315.
Oh, I'm just using a different number. This was completely by chance. I switched problems. Sorry, this is a different problem. Yeah, that's super confusing, my bad.
We thought you were going to use the same one.
That makes sense, because oftentimes I do. I did not. Okay, what do I do with this? Good. And let's see, it's 8 and 1. It gets hot, and it's 9. So, at this question, are you guys okay with the long division-y part of this? If we need practice with it, I can help. Because if you struggle with the numbers, we should talk about it. Okay, right now, the actual answer is 9 a factor of this. Check it out. Yes. And you knew that how? So, good. But check this out. Can you tell me another factor of 351? So you're giving me a bunch of them, but I'm going to give a new one. Is 39 a factor? How did I come up with 39? Holy cow, this is a factor and this is a factor. That's all we're doing, right? We're breaking apart multiplication and we're factoring using this division conceptually. Okay, all of a sudden, this idea is a big one. If the remainder is 0, you found a factor with your divisor. Like 9 was a factor because the remainder was 0. But so is 39. The quotient that I get is also a factor, and we're going to use this immediately. Okay, right off the bat, the ugly section of this, and this is 3.2.3, which we're starting already. Our first section is long division of polynomials. I'm going to say polys. Okay. It turns out that it's pretty much the exact same thing that we just did with a couple little things that we need to be mindful of, and I'm going to help us to make sure that we get these. So hypothetically, I want us to just jump right in with an example. Only thing I'm going to say is pretty much the same as numbers. Can I just say above, because in your notes there's an immediate example above it that's just division with numbers? I assume there's an example right in your notes from just doing long division. Okay. So here we go. We're going to do a couple of these. Did you guys did this last year, I assume? Okay. How many of you think you remember it well? We'll find out. I bet you remember more of it than you think. I want to do the following. Let's try 2x cubed. So I'm just going to say divide, and I'm going to call this example A because we'll do a few of them. We have 2x cubed minus 5x squared plus x minus 8. And I'm going to take that whole mess, and I want us to divide this by x minus 3. All right. Now, two things that I want to be really, really careful for, and we will write this down, but I'm going to say them like I'm a broken record. As we're going through, when I have this thing, my dividend, the thing I'm dividing, it's a cubic, right? Do I have some number x squared or x cubes? I have some number of them. Do I have some number of x squareds? Do I have some number of x? And do I have some constant? If I were missing one, a placeholder would benefit me. And by that I mean if you're missing one, add a placeholder. If this were, don't erase yours, but if this were what I was asking us to divide, and it feels so weird, if it was just 2x cubed plus x minus 8, is there a power missing? And how many x squareds are in this problem? You would write plus 0x squared. You would fill it in. I will repeat and repeat and repeat. So let's try this. I will not give it to you like this again. I'll just write the actual division problem so you don't have to write it twice. Okay, what goes on the outside of the box? So we're going to do x minus 3, and inside the box is that mess, right? 2x cubed minus 5x squared plus x minus 8. All right. It is imperative that you start writing in the correct spot. For this, the first thing in my dividend is 2x cubed. Okay. I'm going to wait till everybody's eyes can go up to this part. I'm going to point to the board. We need to deal with this. In doing division problems, we're just going to subtract to get stuff to fall out. And we just work from left to right, getting stuff to fall out after we subtract. Okay, that's what happened above. This is the important part. The x. That's what we use. Whatever happens with the 3 is just by happenstance. So let's check it out. My goal right now is I want to be able to write under here a 2x cubed because I want it to fall out when I subtract it. So the thought process that I think through it, what do I multiply this by to get me a 2x cubed so that I can subtract it away? X times 2x squared does it, right? Okay, notice x squared has its own spot in this list. When you write your first number, let's go ahead and write it. If it's x squared, we're going to write it above the x squareds. Now, it feels so different, but I promise it's not. I'm going to scroll up again. On this problem, once I wrote the 1 here, how did I get the 31? I just took whatever I wrote and I multiplied it by my divisor, right? We can do the same thing. Let's just what we just wrote, this thing, and multiply it by what? X minus 3. I don't normally draw these lines, but we multiply it to both of them, to the whole divisor. So let's see here. X times 2x squared is what? Minus 2x squared times this 3. Try again. 6x squared. Now it's negative 6x squared, right? Okay. I probably wrote something on our regular number division that you've never done before. What did I put around the number that we wrote here? Subtract it. Now, you can do one of two things. I will always write the parentheses. I encourage you to do it. It would really distribute, right? I think it gets messy if we write it down. I'm just going to make sure I can deal with it as we go. 2x cubed minus 2x cubed. 0. They're gone. Negative 5x squared minus negative 6x squared. What happens with these? They wind up adding. So I'm going to subtract, which winds up adding 11x squared. And how would you like me to drop it? Indeed. Ooh, would it be positive 1? Because negative 5 plus 6. Everybody on board with that? I was so excited to make my stupid Snoop joke. That's my bad. Hate that. Okay. Still hate it. I'm just going to make it x squared because it annoys me. Now can we drop it finally? X squared plus x. Now, remember, which part of this divisor is the part that really matters? The x, the thing in front. I now want what to subtract out of this line? I need the x squared. So in my head, I'm only thinking, don't care about this 3 or that x there, only about the x squared and this x. What do you multiply this by that will allow me to write an x squared right here? Positive x, right? So let's do that. Positive x. And now this x multiplies by the entire divisor. X times x gives me my x squared. X times negative 3. Negative 3x. And I'm going to put parentheses around it for what purpose? Subtract. Everything subtracts. If you're going to make a mistake in a division problem, I would bet like 80% of the time it's going to be from not distributing that negative. If you don't write your negative sign or your parentheses, it doesn't happen. So now we'll just look. This x squared minus x squared. They're gone, right? We did that intentionally. How about this x minus a negative 3x? What happens with them? They add. So how many x's? 4x. And then we need one more.
Why do they add?
Because minus the negative.
Yeah, but if the x on the top is positive, that was the same.
So it's like we're doing this. X minus negative 3x.
Oh, okay.
Yep. Great question. I'm going to drop that negative 8. Now, we can see we're almost done. I now need to get rid of this 4x. What do I multiply by to make this happen? 4. This is the one that we care about. So it's a positive 4. And I'll distribute 4x minus 12, parentheses, and we subtract. And I think it's going to be a remainder of 4. Notice, no decimal. I'm at the end of my list. I can tell I'm done. Do you agree that that essentially just feels like regular division? Okay, there's some big pieces here that I want to make sure we connect. And I'm just going to harp and harp and harp, and I won't quit talking about this throughout this whole section. Okay, there's several different answers here. Our quotient is this guy. This is our quotient. Okay, so first thing that I would naturally ask, is x minus 3 a factor of that larger cubic? You think so? You don't think so? Why? There's a remainder, so check it out. We're just going to make some observations. X minus 3 is not a factor. And I'm not going to write the big one because it's ugly. But this is an important idea. If it were a factor, I now have something smaller in my quotient that's also a factor, and we can start factoring bigger things than you ever have before. Okay, so that's all fine and dandy. Other pieces. The remainder is 4, and I want to go back up here for just a minute. Some of you, how many of you guys did R4 or R5, like exactly like this? Some of you probably did something a little different. Oh my gosh. Sorry. Did anybody ever answer problems like this? The answer on this first problem was 10, and I know the remainder was 5. But do you agree it's 10 and 5 out of how many? Did you ever do it as mixed numbers instead? 5 out of 31, because the 31 is what we're dividing. If I look at this one, there's 4 left over out of, what do we divide by? So when we're really looking at this, our actual answer, when we do this division, real answer, I'm not just going to say true answer, or we'll write real answer, that's fine, that's a little bit too fine there. Real answer, and we'll clarify all this tomorrow, to this division problem was 2x squared plus x plus 4, plus we had a remainder of 4 out of how many pieces were we trying to put in? X minus 3. Okay, this idea leads to a ton of information. Do you guys remember doing this division last year? Do you remember doing it synthetically as well? And you. Okay. You hated synthetic?
I like them.
Ooh, it depends. So they're both valuable in different situations. Now, just so you guys know, like this is obviously division stuff, but the whole driving motivation to this is if we can figure out if something's a factor, we started with x cubed, which we don't know how to factor that. If I knew this was it and this happened to be a factor, I'm now down to x squareds, which are things that we do know how to factor. We're building up the ability to factor bigger and bigger polynomials. Did you guys last year ever use things called PQ lists? That's how I call them. How about the rational zero theorem? I don't remember if it's an Algebra 2 idea or not. More on those things later. Tomorrow you're going to miss a work day with some long division. Okay. All right. Later, Raiders.